Whoa, what is this place?
Welcome to the world of junior college. Here, I'll be your guide for today, so let me show you around. You see, as an A Math prodigy, I've graduated and went on to study H2 Math, which includes
functions, sequences and series, integration techniques, complex numbers, and 3D vectors.
Ow! Ow! Stop throwing books at me. There are so many chapters and I haven't even started preparing for my exam. Please help me, Axolotl Sensei.
It's time for the Math Axolotl to the rescue once again, because I'm gonna go through all the JC1 topics in this ultimate beginner's guide to A-level math. Do you remember how in secondary school for simultaneous equations you have two equations to solve two unknowns? Now we have upgraded into three equations with three unknowns. For this question, we have to find the equation of the quadratic curve, so we let it be ax squared plus bx plus c. Since the question talks about the minimum point, we need to find the derivative, so dy dx is equals to 0, which gives us our first equation. They also said that when x is equals to 2, the gradient dy dx is equals to 5, so that forms our second equation. Lastly, we can sub this minimum point inside the equation of the curve, and that gives us our third equation. Now, after rewriting these three equations like this, we can form something called a system of linear equations. Then we just key in the coefficients of a, b, and c into our graphing calculator to solve for the final values of a is equals to 5/3, b is equals to -5, and c equals to 1/2, and we can get our final answer. For the inequalities question like this, the trick is to shift everything to one side and make it into one fraction. After simplifying and factorizing this quadratic over here, we can get something like this. Now let me introduce you to the idea of a vertical asymptote. Since the denominator can't be equal to 0, x minus 4 can't be equal to 0, so x can't be equals to 4. Then we know that the line x is equals to 4 is a vertical asymptote. Now for the factors at the top of the fraction over here, we can get the x-intercepts of the graph to be x is equals to 1/3 and x is equals to -2. After plotting the graph on your graphing calculator, you can get something like this. Then the region that's below 0 is this region over here and this region. So the final answers are x less than -2 or x in between 1/3 and 4. Now, introducing the modulus function, where it just means that everything in this graph has to be flipped up to be positive. Now, let's not worry about the modulus for now. This quadratic equation over here, we can get the roots of -2 and half, so we know that the graph looks something like this. But since this region over here can't be negative, it has to be flipped up along the x-axis to be positive like this, and ta-da, we have our graph. You know how when we square root something, we always gotta consider the positive and the negative? When solving for a modulus equation like this, it's basically the same, where we have to consider this quadratic equals to positive 2 minus x, or this quadratic is equals to -2 minus x. To solve for x, since this quadratic equation can't be factorized, we have to apply the quadratic formula to get -1 plus or minus square root of 3. Then for this equation, we factorize out 2x and we can get x is equals to 0 or x is equals to -1. For this last part, in order to solve this inequality, let's try to sketch the graph y is equals to 2 minus x on the existing graph, which looks something like this. Since we already saw for the intersection of these two graphs in the previous part, we can label the points of intersection out like this. Now the region where the modulus graph in blue is less than the line in green, which is this region here and this region here. Then we can get our final answer of these two inequalities in this region and in this region like this. Do you remember the inequalities question beforehand? A common extension is to replace all the x with modulus x and ask you to solve it. The trick is to use the solution beforehand and we replace the solutions of x with modulus x and analyze each inequality here. So let's sketch the graph of modulus x and the lines of y is equals to -2, y is equals to 1/3, and y is equals to 4. Since the graph doesn't even touch y is equals to -2, we can reject this. For this part, modulus of x is greater than 1/3, so it refers to this region here, and the modulus of x less than 4 is this region here. So the final answer is this region's in between, which the final answer of x is in between -4 and -1/3, or between 1/3 and 4. There's a common misconception that if a function has a modulus inside, it's always above the x-axis. In order to graph this equation, let's consider the modulus of x minus 5, where we draw the line y is equals to x minus 5 and then flip the negative side upwards. If we take the negative of modulus x minus 5, all of these positive values becomes negative, so the graph kinda gets reflected about the x-axis like this. Finally, the plus 14 at the end means just shifting the graph up by 14 units, and we have our maximum point to be 5, 14 over here. Introducing the piecewise function, which basically follows this equation when x is in between 0 and 2, and this equation when x is between 2 and 4. And this f of x is equals to f of x plus 4 means it's a periodic function, where the graph repeats itself every 4 units of x. So for example, the value of f of 1 is equals to the value of f of 1 plus 4, which is f of 5. To find f of 27, we have to keep counting 4 units backwards, so 23, 19 and so on, until we reach 3, which is in this range over here. So calculating f of 3, which follows the 2x minus 1 function, we can get 5. Let's do the same for f of 45, and counting backwards, we can see that it's equals to f of 1, which follows this function, and we get the final answer of 6. In order to sketch this graph, we have to find the starting and ending points of these two parts of the function here. So putting x is equals to 0 and x is equals to 2 into y is equals to 7 minus x squared, we can get the starting point of y is equals to 7 and the ending point of y is equals to 3. So let's do the same for the other part of the function, and we can get the starting point of y is equals to 3 and the ending point of y is equals to 7. Now plotting it onto the graph, since y is equals to 7 minus x squared is a set-face quadratic, it kinda looks like this, and 2x minus 1 is a straight line, so it looks like this. Notice that the ending point of this part connects to the starting point of the next part, so we can say that this is a continuous function. This topic is all about the idea of asymptotes, which is an imaginary line the curve approaches but never crosses it. In order to sketch this graph over here, if it's an improper fraction, the first step is to always do long division, and we get y is equals to 4 plus 1 over x plus 2. Since we know that the denominator can't be 0, x equals to negative 2 is a vertical asymptote. If we look at 1 over x plus 2, this whole fraction can't be equals to 0 since the numerator doesn't have any x terms. Therefore, we know that y cannot be equals to 4, therefore y is equals to 4 is a horizontal asymptote. The last step is to draw our asymptotes and then plot the graph like this using our graphing calculator. Now for this equation here, similarly, since the denominator can't be equals to 0, x equals to negative 2 is a vertical asymptote. And since 1 over x plus 2 can't be 0, y cannot be equals to 2x plus 1. Now since y is equals to 2x plus 1 is a straight line equation, we call this an oblique asymptote. Now we just draw the vertical and oblique asymptote and the graph should look something like this. Let's take a look at this ellipse graph, which kinda looks like a circle equation. Now the radius in the x direction, comparing it with the general formula, a is equals to 5, and the radius in the y direction, where b is equals to 3. I'm gonna draw this new ellipse here, where everything is the same, but the center is at 2, 4, and we ask ourselves, how do we transform this graph to make it look like this? The obvious solution is just to shift the whole graph right by 2 units and up by 4 units, and this is what we call a translation. So here's the tricky thing about translations. You always gotta think the opposite way. So since x is translated 2 units in the positive x direction, x has to be replaced with x minus 2. And similarly, since y is translated 4 units in the positive y direction, y is replaced by y minus 4. And then comparing this with the general form of the ellipse, we can get the coordinates of our center. Wanna see something really weird? If we just change this plus sign to a minus sign, the graph completely changes shape and it looks something like this, which is a hyperbola. Now comparing it with the general form, the center is at 2 and 4. If we take a look carefully, the graph actually has 2 oblique asymptotes, and each one of them has a gradient of plus minus b over a. So this asymptote here has a gradient of 3 over 5, and this has a gradient of negative 3 over 5. and since both of them pass through the center of 2 and 4, we can construct the equation of these two lines by subbing in this point and solving for c. The last thing to note is that the distance between the center and this point is a, which is 5 units, so this point here is -3, 4, and this point is 7, 4. Let's put it all together for this question where we have to determine the values that this curve cannot exist. We sort of get the hint that the discriminant has to be less than 0. So after simplifying this equation into the quadratic form in terms of x, we can do b squared minus 4ac is less than 0, and after doing a quick sketch, the region that is less than 0, we can get the values that y cannot take to be in between 1/6 and 3/2. Let's first identify the asymptotes to sketch the graph. So looking at the denominator, x cannot be equal to 0, and x cannot be equal to -6. As x approaches positive infinity, we notice that y approaches 0, and since this equation can be reduced to the 1/infinity form, y is equal to 0 is a horizontal asymptote as x tends to infinity. We can also get our stationary points over here by using our graphing calculator or equating dy dx is equal to 0. Finally, we mark out all our asymptotes, then our stationary points, and then we can draw the graph like this. For a question like this where they ask you to transform one graph into another, we always try to replace either x or y with something, and then we start from the inside. So let's start with replacing x with x minus 3. And remember that it's kind of in reverse, so it's a translation of 3 units to the right. The next one is quite tricky where we try to introduce this 1/4 here, so let's try to replace y with 4y. So again, everything's kind of in reverse. We are scaling the y-axis with a scale factor of 1/4, where the y-axis kind of gets squished together, causing the graph to widen. Now the last step is to introduce this negative, so we replace y with -y. This idea basically reflecting the graph about the x-axis, where whatever is up here gets reflected down here and then we are done. This question asks about how these points here and here will change if certain transformations are done to the function. So to visualize this, let's consider some random graph like y is equals to 1 minus x, and we want to replace x with 2x. So the equation becomes y is equals to 1 minus 2x. So after sketching that out, we can see that the graph kind of gets squished together in the x direction, so the new x-intercept becomes a/2 and the y-intercept remains the same. For part B, let's try to replace x with x minus 1, and we draw out the new equation y is equals to 2 minus x. You can see that the whole graph gets shifted 1 unit to the right, so on the point of the x-axis it becomes a plus 1, and this y-intercept here becomes x is equals to 1 and y is equals to b. And since this point over here is not the y-intercept anymore, we have to reject this point since we don't know what is the real y-intercept. For the last part, using f of x minus 1, we are going to replace x with 2x. Note that we can't do it the other way around using f of 2x, since if we replace x with x minus 1, we don't get 2x minus 1. So let's draw out the f of x minus 1 graph like this, and then we replace x with 2x, and then it squishes the graph in the x direction by half. So the new x-intercept becomes a plus 1 over 2, and the point 1, b, the x value will be squished to half, b, but again we have to reject this since it doesn't lie on the y-axis. Now, this question I feel is one of the most difficult kind, where they give you an unknown graph f of x, and they ask you to sketch y is equals to 1 over fx. Okay, let's start with the asymptotes first, and since f of x can't be equal to 0, and since it's at the denominator, we notice that this x equals to minus 3 here, f of x is equals to 0. So we know that x is equals to -3 is a vertical asymptote. We also notice that when x approaches infinity, f of x approaches 10. So since y is equals to 1 over f of x, the new y will approach 1 over 10. So y equals to 1 over 10 is our horizontal asymptote. Okay, let's take a look at the original graph's x equals to -2 asymptote here. As x approaches -2, f of x approaches infinity, and since y is equals to 1 over f of x, 1 divided by infinity is 0. So we can plot the point x is equals to -2 and y is equals to 0 here. Then taking a look at this turning point A, since the x-coordinate doesn't change, the new y-coordinate is 1 divided by 4, and let's plot this point over here. The last point to plot is the original y-intercept of 0 and 6, and now the new y-intercept is 0 and 1 over 6. The last step is to take a look at the x is equals to negative 3 asymptote and take a look at a point slightly to the left and to the right. So to the left, let's say the y value is 0.01 and on the right is negative 0.01. For the left part taking 1 over 0.01, we get positive 100, which corresponds to a point up here, and on the right, we take 1 over negative 0.01, which gives us negative 100. Then we know that the graph goes up to 100, and then it starts again from negative 100 way down here. Next, for the same graph f of x, let's try to draw the graph of the first derivative f prime of x. Since we know that this point x is equals to minus 1 here is a turning point, we know that f prime of x is equals to 0 at x equals to negative 1. So we can plot this point over here. Now since f prime of x cannot be equal to 0 at any other point other than the turning point, y is equals to 0 is a horizontal asymptote. Okay, the last step is to figure out the shape of the graph. So at this part of the graph, any tangent you draw is sloping downwards, so we know that f prime of x here has to be negative. Now to the right of the asymptote, it's also sloping downwards, so f prime of x is negative, and after the turning point, it's sloping upwards, so f prime of x becomes positive until it's almost horizontal, so f prime of x approaches 0. Then we draw out the graph and it should look something like this. Okay, this meme needs to be in every math textbook out there that's teaching about inverse functions. But before I show you how to inverse a function, we have to check if a function has an inverse in the first place. The first step is to draw out the graph f of x, and since we're only looking at x greater than 1, it looks something like this. Now introducing the horizontal line test. So if we draw a horizontal line like this anywhere, it should cut the graph of f of x at most once, which this graph does. But if it cuts it twice like this, that means the inverse doesn't exist. Now, finding the inverse of a function is just like turning the function inside out, where we are trying to make x the subject of the formula. So after shifting x squared to one side and combining these two terms, we square root both sides to get x is equals to plus minus square root of y minus 1 over y. Now because of our domain is x greater than 1, we can only take the positive root. So we replace all the y's with x's, and then we can get f inverse of x to be square root of x minus 1 over x. If we take a look at the graph of f inverse of x over here, you can see that it's symmetrical about the line y is equals to x. So to give an example, a point on the x-axis like 5, 0 for f of x will be flipped over to the y-axis at 0, 5 for f inverse of x. So therefore, we can say that the range, which is the y values that f of x can take, will be transformed into the domain, which is the x values of f inverse of x. If we look at f of x, we can see that all the y values that it can take is anywhere from negative infinity up to 0 because there is a horizontal asymptote. So this will be the x values that f inverse of x, which is also from negative infinity all the way up to x is equals to 0, which is this vertical asymptote over here, and you can see that in the graph. For this question over here, in order to find f of x, it's kind of like making f of x, which is 1 plus root x, the new x value in the outer f of x, and we know that all of this is equals to x. Now shifting the 1 over to the other side, we can get something like this, and notice that since this must be greater than 0, we can get the condition that x minus 1 is greater than 0 as well, so x is greater than 1. Now, after squaring both sides and then squaring both sides again, we can get something like this, and factorizing out x, we can get a cubic equation, and then we can use our GC to solve for the values of x to be 2.62 or 0.38. Since x is greater than 1 from just now, we have to reject 0.38 and 0 as a solution. Now the last step is to prove this equation over here, and let's take a look at f of x is equals to x, and let's try to take the f inverse on both sides. There's a really neat little trick that, for example, if you take the f inverse of f of x, your f inverse and f kind of cancels out, and what you're left with is x. For this question, again, the f inverse and the f cancels out, and what we are left is whatever's on the inside, which is f of x, and we managed to prove that f of x is equals to f inverse of x. Now, introducing the idea of composite functions, where in this case we have the composite function of g of f of x. So drawing out a simple diagram, g of x has to take on whatever values that comes out of f of x. For a function, what goes into the x value comes out the y value. So in order for gf to exist, looking at this over here, the y values that come out of f of x has to be a subset of the x values that g of x can receive. So we can say that the range of f has to be a subset of the domain of g. After drawing out both graphs like this, for f of x we can see that the possible y values are from 2 to 3. Now for g of x, the possible x values that it can take is from -1 over here to infinity. After drawing out a quick number line like this, we can see that indeed the range of f is a subset of the domain of g. The last step is to download Tinder to find gf. So we put e to the power of -x plus 2 into gx, and we can get gf is equals to -ln e to the power of -x plus 3, where x is greater than 0. In order to find the range of gf, there's two methods. The first is to draw the graph of gf and to find the y values that it can take. But let's focus more on the second method, which I call the applying the function to the extremes. Since f goes into g, the range of f is from 2 to 3. Then we just have to apply g of x to 2, which gives us -1.1, and we do the same for 3, which we get -1.39. Finally, the range of gf is just from -1.39 to -1.1. A sequence is just like a number pattern, so for this question, each term is connected to the previous term by this formula, which is called a recurrence relation. So let's try to let n is equals to 1 to see the base case, and we can get an equation like this over here. Since u1 is equals to 5 and u2 is equals to 15, let's put these values in and we can solve for our unknown a, which is 5. Now the final step is to just let n is equals to 2, and putting all the values in, we can get the final answer of u3 is equals to 40. Let's try a more difficult recurrence relation question, where if n approaches infinity, xn approaches theta, and using the same logic, xn plus 1 also approaches theta. So let's replace xn and xn plus 1 with theta inside this equation, and we square both sides. We can then factorize this cubic equation, and since theta can't be negative, we can use the quadratic formula to get the solution of 2.22. Now, if we want to sum up the first n terms of a series, we can write it like this, or we can use the sigma notation, where we have this variable r here, which sums up the terms from r is equals to 1 to r is equals to n of whatever's inside here. So for this question, if n goes to infinity, we can see that n plus 1 factorial also goes to infinity. But remember that a number over infinity will approach 0, so the sum to infinity is just 1 minus 0, which gives us 1. So imagine if we want to find the value of u4, we can just take the sum s4 minus s3. So similarly, if we want to find un, we can take sn minus sn minus 1. So putting that into our expression, we can get something like this. Then the next step is to try to combine these two fractions. So for n factorial, we can multiply the top and the bottom by n plus 1 to get the denominator to be n plus 1 factorial. Then the final answer is just n over n plus 1 factorial. Now for this question, we can first notice that the denominator is in the a square minus b square form, so let's rewrite it. And we try to split this up into partial fractions like this, which you'll see why in a minute. So after constructing the equation and solving for a is equals to -½ and b is equals to half, we can kind of factorize the half outside of the summation, and let's try putting r is equals to 1 inside, which gives us 1 over 1 minus 1 over 3. And for r is equals to 2, it gives us 1 over 3 minus 1 over 5 up to r is equals to n, which gives us 1 over 2n minus 1 minus 1 over 2n plus 1. Now, are you ready to see some magic? We can notice that this minus 1 over 3 here and this 1 over 3 kind of cancel off. So does this minus 1 over 5 and this plus 1 over 5, and you start to notice a pattern. Everything on these diagonals over here will cancel off with each other until we are left with just two terms, 1 over here and -1 over 2n plus 1 over here, and that is our final answer. This is called the telescoping series, and I think it's one of the coolest things in math. To find the summation from r is equals to 11 to infinity, we can take the summation of r is equals to 1 to infinity minus off the summation from r is equals to 1 to 10. Because we found the summation in terms of n in the previous part, we don't have to use the summation anymore, and we can just sub in n is equals to infinity for this, and n is equals to 10 for this. For this fraction, again, it's 1 over infinity, which approaches 0, so the final answer will just be evaluated out to 1 over 42. Are you ready for the ultimate sigma question? The first step for part A is to split up the series, and looking at this part, since r starts from 0 up to n, it's basically n plus itself, n plus 1 times. For the other summation, writing it out, notice that we can sort of factorize out the n plus 2, and what we're left with is the sum of 1 to n, which is n bracket n plus 1 over 2. So putting all of this together and simplifying the expression, we can get the final answer of n over 2, n plus 1 times n plus 4. For part B, let's try to write out the first few terms and the last few terms of this summation, and notice that r starts from 3 and ends at n plus 2, so it can be written as a summation like this. But if we take a look at the summation given, it starts from r is equals to 1 and goes up till n only. So we have to make a few changes. Since it goes up to r is equals to n plus 2, we need to replace n with n plus 2. And secondly, since it doesn't have the r is equals to 1 and r is equals to 2 terms, we need to minus off 1 cube and 2 cube respectively, so the final answer will look something like this. Now for the last part to express this sum, we try to whack our best guess, so it starts from 1 cube and 2n cube, so let's try r is equals to 1 and 2n. But notice that every even term is a negative, so let's try to find a summation for just the even terms. So if we sum up from r is equals to 1 to n, but notice that if we sum the whole bracket of 2r cubed instead, we can get all the even terms from 2 cubed all the way up to 2n cubed. The magic happens when you see that this summation minus 2 times of this summation will just give us the answer. So we factorize out the 2 cube here and replace it with n with 2n for this summation, and we can get our final answer. This question talks about some guy running from O to A1, then back to O, then to A2, and so on, kind of like a shuttle run. Because he needs to run there and back, the total distance is 2 times of 4 plus 8 plus 12 plus 16 and so on. So this kind of number pattern is actually called an arithmetic progression, because they have a common difference of 4, and we call the first term A over here. So here are the formulas that you have to remember. We gotta use the sum to nth term formula to find the total distance, which is just 2 times the sum of the first 10 terms. So finding S10 by putting A is equals to 4 and the common difference D is equals to 4 and multiplying it by 2, we can get the total distance of 440 meters. To find an expression for the first n stages, we can use the same formula, subbing in a is equals to 4, but leaving n as our unknown over here, and we can get 4n squared plus 4n. The last step is to say that this distance over here has to be greater than 5,000, and we basically have to solve the inequality using the quadratic formula, and we can get n is greater than 34.9, and therefore the final answer is 35 stages. For this separate race, we can see that the total distance ran is 2 times of 4 plus 8 plus 16 plus 32 and so on. This time we call it a geometric progression, since instead of a common difference, it's times 2 and so on, so we can say that the common ratio is 2. These are the formulas to remember, but we only need to use the sum of n terms formula for this question. Now, the total distance is just 2 times of the sum to n, and putting in the common ratio of 2 and a is equals to 4, we can get negative 8 times 1 minus 2 to the power of n. Just like before, we can let this to be greater than 10,000, and we can just log both sides to solve for n to be greater than 10.29, and the final answer is 11 stages. The most popular kind of geometric progression problems are these compound interest ones. Since the interest rate is 5% and John puts in X dollars every year, in the first year it grows from X to 1.05x. Then on the second year he adds in X dollars as well, and we multiply this whole thing here by 1.05, and the pattern repeats. Looking at the end of year 3, we can notice a pattern where each term is multiplied by 1.05 and the first term is 1.05x. So let's put these values in our Sn formula to find the sum of n years, and after simplifying it, we can get 21x times 1.05 to the power of n minus 1. And given that x is equal to $10,000, we can use this to construct an inequality like this to solve for n. Taking the log on both sides, we can estimate the value of n to be greater than 24.9, so therefore it will only exceed $500,000 at the end of the 25th year. This example is a little more challenging, where Sarah puts in $6,000 in the first year and then invests $400 more in the next year and so on, making it pretty complicated, and it's harder to see the pattern here. At the end of the third year, n is equal to 3, so let's analyze each individual term. In a summation starting from the first term, r is equal to 1 and so on, let's take a look at this term where r is equal to 2. So there's only like 1 of the 400. So we know that it's r minus 1 times 400. And the power of 1.05 is 3 minus 1, so we can rewrite this 1 as r minus 1 as well as n minus r minus 1. Then just doing the comparison, a is equals to 6,000 and b is equals to 400. So putting all this in a graphing calculator, we can again look for the sum from year 1 to year n where the amount is greater than $500,000. So we can see over here that at year 26, she is officially half a millionaire. Unlike me. This question is really interesting, where the first, second, and third term of a geometric series is equal to the first, seventh, and 10th term of an arithmetic series. Since both first terms are the same, let's call them a, and for the arithmetic series, the 7th term is a plus 6 times of the common difference d, and the 10th term is a plus 9d. For the geometric series, since it's multiplied by r, the second term is a times r, and the third term is ar squared. Since these are the same, let's replace the geometric series with a plus 6d, and a plus 9d as the first, second, and third term. Because one term to each other, they have the same common ratio, we can just do the second term over the first term is equals to the third term over the second term, since the ratios are the same. Then we just cross multiply, and after solving using some algebra, we can get d is equals to 0, which we have to reject, or a is equals to negative 12d. Now, something important for the sum to infinity formula is that the series only converges to a certain value if r is from negative 1 to 1. So let's try to find the value of r by looking at these two terms which are equal to each other. After dividing the whole equation by a, we can get a is equals to negative 12d, and you can see that the d kind of like cancels each other off, giving the value of r is equals to half. Now, since the sum of infinity is equal to 1, we can solve for the d of the arithmetic series to be negative 1 over 24. So welcome to the new and improved idea called implicit differentiation. If you look at this equation, you can notice that it's no longer in the y is equals to fx form. So we have to take the derivative with respect to x of every single term in this equation. Let's try to differentiate x squared y using the product rule. So differentiating x squared gives us 2x, and we keep the y, plus x squared, and now here comes the problem on how to differentiate y with respect to x. The trick is to just pretend to differentiate this with respect to y, so it becomes 1, but importantly we have to multiply a dy dx to it. Now differentiating the product of x y squared, it's 1 times y squared plus x times differentiating y squared, we get 2y, and then we remember to slap on the dy dx. Then the next step is to just move all the x and y terms to the other side, keeping the dy over dx terms on the left side. We can just kind of factorize out the dy dx by dividing both sides, and finally we have our derivative with respect to x. After letting dy dx to be negative 1, since it represents the gradient, we can get the two solutions of y is equals to x and y is equals to negative x. So using these solutions, we have to sub it back into the equation of the curve, and for the y is equals to x equation, we can actually solve for x to get the value of negative 3, and since y is equals to x, the y value is negative 3 as well. For the other equation, subbing it in, we notice that 54 is equals to 0, so it's invalid, and we have to reject this, and the final answer is the point negative 3 and negative 3. Parametric equations are where x and y are not dependent on each other, but dependent on some extra variable t instead, kind of like a marriage affair. The first method to solve them, I call it the eliminating t approach. So I'm gonna make t the subject of the formula for this equation and then sub it into the other equation. So in order to save the marriage and express y in terms of x, and we get the equation of y is equals to 6 over x. Now, using this equation of y in terms of x, we can solve it simultaneously with y is equals to 2x in order to find the points a and b. So after getting x is equals to plus minus 3, we can get the corresponding y value of y is equals to plus minus 6 over root 3 as well. And using this, we have our coordinates of a and b. The last step is to find the length of AB, where we can just use the distance formula and we can get the square root of 60 units. In order to sketch out a graph of a parametric equation, we first need to find the x and y intercepts. So we let x is equals to 0 and our goal is to find the corresponding y coordinates. So solving for it, we get t is equal to 0 or t is equals to negative 1. Now the important thing is that we need to sub these t values into the y function to get the corresponding y values. So x is equals to 0, y is equals to 0 is 1 point, and so on. Then we just repeat the same for y is equals to 0 and subbing it into the x equation to get the following coordinates, we just plot it on the graph and connect it with a curve. The other method to solve parametric equations is what I call the rate of change method. Since x and y are in terms of t and they are relatively easy to differentiate, we can get the values of dx over dt is equals to 6t and dy over dt is equals to 6. Then we can construct the rate of change equation like this, and we can solve for dy dx to be 1 over t. Now since we know the gradient of the tangent is 0.4, we can just solve for t to be equals to 2.5. You might be familiar with these kind of optimization problems in A Math where it's broken down for you, but in the A levels, you're on your own, kid. The first step is to know that we have to make dv over d something is equals to 0 to find the maximum. So let's equate the surface area of the cylinder to 900 as given in the question, and the trick is to find an expression for h, and it gives us something like this. Now we want to sub this value of h into the volume formula to eliminate it, and you can see that v is in terms of r. We can then differentiate it to get dv over dr to be 450 minus 3 pi r squared, and let's equate that to 0. And then we can solve for the value of r to be square root of 150 over pi. We can finally sub this into the volume formula to get the volume of 2073 cm cubed, and after working out the second derivative of v, we can see that it is less than 0. So therefore we know that v is a maximum. Let's try this question where a cylinder is inscribed inside a sphere. So since this question gives a hint to express a in terms of x and r here, we try to get rid of h. So using Pythagoras, we can get h is equals to 2 square root of r squared minus x squared. Since we know that the curved surface area A is equals to 2 pi xh, we can sub the value of h inside, and instead of just differentiating A with respect to x, let's square all the terms here, and we can actually perform implicit differentiation, and using the product rule over here, we can get something like this. So after equating dA over dx to be equal to 0, we can get x is equals to 0, which we have to reject, or r squared is equals to 2x squared, which we want to solve for x to get x is equals to r over square root of 2, where the negative value is rejected. So let's try to perform the first derivative test this time, where we notice that our dA over dx function only depends on r squared minus 2x squared, since this front part over here is always positive. So sketching the graph of this function, we can analyze this stationary point over here, where to the left of it, dA over dx is positive, and to the right of it, it's negative. So we know that it is a maximum. Welcome to the new McDonald's series, where every special occasion, they release their new selection of burgers and seasonal items such as... Okay, let's get back to talk about the Maclaurin series, where instead of a new series of burgers, each of these terms can be approximated by a series that's found inside your formula sheet. For this question, let's try to refer to the Maclaurin series of e to the power of x and ln of 1 plus x, and notice that in this question, it's e to the power of 2x and it's ln 1 plus ax. So putting these in as our new values of x, expanding up to the x cubed term, we can get the expansion of something like this. Finally, we can just expand out everything and we get our final expression. For the next part, since the question says that there is no x squared term, we can equate the coefficient of x squared to be equal to 0, and since the value of a cannot be equal to 0, we can solve for the final answer of a is equals to 4. This question is a little bit more difficult, where we try to prove this differential equation over here. So differentiating y, we can use the derivative of sine inverse of x found in the formula sheet to get 1 over the square root of 1 minus x squared times e to the power of sine inverse x, which we have to rewrite this as y, and let's simplify this by multiplying the whole equation by the square root of 1 minus x squared. Let's call the original equation 1 and this new equation 2. Now from here, seeing that there's a second derivative in the original equation, let's try implicit differentiation, where we differentiate all terms by x, and using the product rule on this over here, again we multiply the whole equation by the square root of 1 minus x squared, and we manage to prove this equation, which we call equation 3. Okay, let me introduce you to the general Maclaurin series, which looks something like this, and since they want us to find up to the fourth term, we know that we gotta find the third derivative. So doing implicit differentiation again, and this time using the product rule on this, and that gives us this crazy looking equation over here, which we call equation 4. Okay, now, are you ready for some magic? Since f of 0 represents y and f prime of 0 represents dy dx and so on, let's first sub x is equals to 0 into equation 1 in order to solve for y, which gives us y is equals to 1. Now using this value, let's sub x is equals to 0 and y is equals to 1 into equation 2, and we can get dy dx is equals to 1. Then using all of these values, we can find the second derivative, and that also equals to 1. And finally, subbing everything into equation 4, we can get our third derivative to be equals to 2. Then the last step is to just construct our Maclaurin series, and it looks something like this, and we are done. Whenever an angle is small, we can use these things called small angle approximations, which I've seen so many times studying engineering, and I can confirm this meme is 100% accurate. For this question, since it's a right-angled triangle and we want to find QR, we can do cosine theta, and we're gonna apply the small angle approximation to cosine theta. Then using the Maclaurin series of the binomial expansion, where n is equals to -1, we only need to consider the first two terms, since this question says that theta cubed and above terms can be neglected, and we managed to prove that QR equals to half r theta squared. Do you know one of those memes where the boat is sinking and you just slap on a piece of duct tape and everything's fine? Well, that's basically the u substitution method. The first step is to just differentiate u to get du dx, which works out to be 1 over 2 square root of x plus 2. Then we just kind of shift the dx over, kind of like a fraction, to get an equation like this. Now, this is where the magic happens. We want to look for this inside our integral, which we can kind of see over here. So let's split up the fraction inside our integral, so we are looking for 1 over 2 square root of x plus 2, but we only have 1 over square root x plus 2. So we gotta do this trick where we multiply this by 2 and divide this by 2 because it kind of cancels out. Now you can see that all of this is equals to du, so let's replace all of this by slapping on a du over here. Since now we are integrating with respect to u, we rewrite x in terms of u, which is x equals to u squared minus 2, and then sub it in and perform our integration. Then the final step is to just replace all the u in terms of x like this, and then we are done. Here's a more difficult substitution integral, where our goal is to change everything in terms of theta. So differentiating x, we can get dx is equals to 3 cosine theta d theta. Now notice our integration limits. This represents x over here and also needs to be converted to theta. So solving for theta, we can get the new limits of pi over 6 and 0. Now after substituting dx and x into the equation in terms of theta, we can use the trigo identities to convert this in terms of cosine squared theta and the double angle formula to change it to cosine 2 theta. Then after integrating and putting our limits in, we can get the final answer of 4.30. Okay, the next integration technique is called integration by parts. This is gonna sound crazy, but it's kind of like a redox reaction, where you differentiate one and then you integrate the other. So u will be the one that we differentiate, and we let u is equals to x because differentiating it will kind of reduce the equation down and make it simpler. Then the rest here will be dv. So let's differentiate u to get du is equals to dx, and integrate dv to get v, which gives us 2x plus 1/4 cosine 4x. Now, putting it into our integration by parts equation, this is the part that we are interested in. We gotta now rewrite this du in terms of dx. So for this case, du is equals to dx. And we ask ourselves, can we integrate this? If the answer is no, we probably messed up and gotta swap our u and dv. Or we need to do integration by parts one more time. But for this case, we can just integrate this portion here with respect to x, and we can get our final answer like this. Let's move on to integration by standard forms, where this is the standard form for the e to the power of x integration. Let's try to turn this equation into this form. So since f of x is equals to 3x squared plus 1, f prime of x is equals to 6x. Then we just want to turn this x over here into 6x. So we multiply the outside by 1 over 6, and this becomes 6x, so it cancels out. And then we have our final answer. This can also be done using u substitution, where if we let u is equals to 3x squared plus 1, you can see that this 6x dx here can be written as du instead, which gives us the final answer as well. This question looks a little bit tricky to integrate, so let's try to split apart these two fractions like this and like this. Introducing the second standard form, which is the f prime of x over fx kind. So in this case, f of x is equals to 4x squared plus 16, and f prime of x is equals to 8x. So again, using the same trick, we multiply 1 over 8 on the outside, and this becomes 8x, and after integrating it, we can get 1 over 8 ln 4x squared plus 16. The next one requires you to look at the formula sheet, and since it resembles a tangent inverse form over here, after factoring out 1 over 4 to make sure the coefficient of x squared is 1, we can rewrite this as x squared plus 2 squared, and after integrating, we can get the form of 1 over 8 tangent inverse x over 2. The last standard form question looks really similar, but if you notice, there's no way to make it into the f prime x over fx form. So the trick is to actually complete the square at the bottom, so we can get x plus 3 squared minus 3 squared plus 13, which gives us x plus 3 squared plus 2 squared, which corresponds to the tangent inverse standard form that we did earlier. And then after integration, we can get our final answer like this. This question is an integration by parts in disguise, since there's only tangent inverse x. So we can say that u is equals to tangent inverse x, and dv is just equals to 1. So differentiating u, we can get du is equals to 1 over 1 plus x squared dx. And integrating 1 to get v is equals to x, we can sub everything into our integration by parts formula, and let's figure out how to integrate this. Notice that when we differentiate 1 plus x squared, we get 2x, which is very close to the numerator x, so we know that it's a f prime x over fx form. So we just multiply a 2.5, which cancels each other out, and we can get our final ln integral like this. Have you ever wanted to create a Hershey's Kisses using integration? Well, because we're gonna do that in this question. For the first part, since we have cosine cubed of t and sine cubed of t, let's try to make use of the identity that sine square plus cosine square is equals to 1. Since we want cosine square, let's raise the power on both sides by 2/3, and we can get cosine square of t is equals to x to the power of 2/3. Then we do the same for the sine square term, and finally let's put all of that into the identity, and we've proven the first part. After doing a quick sketch of the graph, this is the region bounded by the curve x equals to 0 and y is equals to 0. Since the question asks for the volume of rotation about the y-axis, you can see that you will get the Hershey's Kisses shape. Now this is the formula for the volume of rotation with respect to the x and y-axis respectively. Since we're integrating with respect to y, we have to make x the subject of the formula first. Notice that the function in the formula to integrate is squared, so our goal is to get x squared. So let's cube both sides of the equation to get x squared, and now it's time to expand this part here using the binomial theorem. After some algebra manipulation, we can get something like this, and we are ready to integrate. Putting all of this inside, we can integrate with respect to y from y is equals to 1 here to y is equals to 0 here. And after doing the integration and putting in the limits, not forgetting to multiply this pi in, we can get the final answer of the volume to be 0.479 units cubed. Okay, it's time for the bonus round, which I call this one the rectangle approximation integration question. So let's set n is equals to 5 and sub it into the equation, and it will look something like this. If I draw a random graph of f of x at 1/5, we can get the height of the rectangle to be f of 1/5, and so the area of this rectangle over here is 1/5 times f of 1/5. And after adding up all the areas of the rectangles, we managed to get the equation that we came up with just now. Therefore, as n approaches infinity, we have infinitely thin rectangles, and the area of all the rectangles will just be the integral from x is equals to 0 to x is equals to 1. Even though this topic is called differential equations, it's actually more related to integration than differentiation. This is a differential equation over here. Now, y equals to x squared is a solution to this differential equation, since taking the derivative on both sides gives us dy dx is equals to 2x. If you notice, y equals to x squared plus 5 is another solution because differentiating this also gives us the same thing. So let's try out this question, and the trick is to separate the variables by shifting all the y terms on one side and all the x terms on the other side, kind of like this. And the last step is to shift the dx over kind of like a fraction. Now we can integrate both sides, this side with respect to y and this side with respect to x. And also don't forget your plus c. This is called a general solution since we haven't solved for the unknown constant. So for part B, subbing in these values into the equation, we can solve for c is equals to -3, and this is called a particular solution because it is the only one. These kind of population modeling questions are super popular. Since P is the population of sheep and is declining by 3% every year, the rate of change of the population over time is negative, so dp over dt equals to -0.03p. Again, we can use the separation of variables method, and then we can integrate both sides to get something like this. Since p is greater than 0, let's try to get rid of the ln using our logarithm laws, and we can get p is equals e to the power of -0.033t plus c. Because we don't want the unknown constant at the top, we split apart the powers of e by using our indices laws and rewrite e to the power of c as a new constant a, and then we are done. Notice when t approaches infinity, the value of e to the power of -0.03t will approach 0. So therefore, p will approach 0 as time passes, which means that the sheep will go extinct over time. In part B, since they decided to import n number of sheep every year to keep the population going, so the differential equation becomes dp over dt is equals to -0.03p plus n. Again, we do our separation of variables method and integrate both sides like this. Since we are integrating with respect to p, we have to divide by -0.03, and we can get rid of the ln using our logarithm laws and splitting the powers of e up and rewriting this as our unknown constant b. We can remove the modulus by making b is equals to plus minus e to the power of -0.03c. And after simplifying, we can get our final equation for the population over here. Notice that this time, as t approaches infinity, e to the power of -0.03t approaches 0, so therefore p will approach 100 over 3n. For example, if n is equals to 15, new sheep are added this year, p will approach a stable population of 500, and then the sheep will not go extinct. Yay, go sheep! Woo! Now this question is a little bit more difficult since we can't integrate this because of the square root v term, so we have to use a substitution. And finding dv over du is equals to 2u, we can construct the chain rule where our goal is to split apart du over dt. So putting the values of dv over du that we found previously and dv over dt that's given in the question, we can shift all the u terms to one side and then factorize out the 2. Then we can multiply the numerator by k and factorize out 1 over k in order to make it in this form given in the question hint, which uses partial fractions to make it such that we can integrate these two terms over here. After doing the integration on both sides, we can change back all the u terms to square root v and multiply the whole equation by 2k in order to achieve the final form that's given in the question over here. Learning complex numbers is kind of like the first time you found out negative numbers actually existed. The imaginary number I is equal to the square root of -1, and because of that, squaring both sides, I squared is equal to -1, and it suddenly becomes a real number. A complex number can be split up into its real part and its imaginary part. So imagine we have a complex number z is equal to 3 plus 4i, then its conjugate z star is equal to 3 minus 4i. And now, let me introduce you to the Argon diagram, where this is the real number axis and this is the imaginary number axis, so z and w can be drawn like this and this respectively. The modulus for each of these is really simple, where it's basically Pythagoras' theorem to find the length of this line, so the modulus of z is 5 and the modulus of w is 2. For the argument, it's different for the top half and the bottom half. So at the top half, it's the positive angle from this line to this line in the anti-clockwise direction. And for the bottom half, it's the negative angle from this line to this line in the clockwise direction. So the argument of z is just the tangent inverse of the opposite over adjacent, which gives us 0.93 radians. To get the argument of w, we first need to find alpha by using the same method, and alpha is equal to pi over 3. Since this is the negative direction, the argument of w is negative pi plus pi over 3, which gives us the answer of negative 2 pi over 3. Let's try out the first part of this question, where we write out the complex number z and z star, where we just sub it into our equation. Now what we have to do is just to compare the coefficients of the real parts and the imaginary parts on the left hand side and the right hand side and equate them to each other, so we can get a is equal to -1 and b is equal to -4. For the next part, after subbing in the values of w and z, we notice that there's a fraction here. We have to realize this fraction, which is kind of like rationalization, where we want the denominator to become fully real, so we multiply the top and the bottom by its conjugate. After doing some simplification, we can get the final answer of 2 plus 6i. The problem with solving this simultaneous equation right now is that we can't make z or w the subject or formula because they all have imaginary coefficients. So our goal is to try to make the coefficient of z real by multiplying I throughout equation 1, and since I squared is -1, we can get z is equal to w plus half iw minus 2i, which we call equation 3. Then we can just sub equation 3 into equation 2, and after some expansion, we can solve for w is equal to 2 plus 4i over 5 plus 5i. Then the last step is to just realize this fraction, and we can get our final answer of 3/5 plus 1/5 i. Now for this question, when we want to verify that something is a root to an equation, we kinda just sub in the value and verify that for here it equates to 0. So let's sub in -1 plus 5i inside our equation, and after doing some expansion, we can see that it indeed equates to 0. The next part is talking about finding the second root, which requires us to compare coefficients. So let's rewrite the quadratic as this, where we have found the first root over here and the second root c over here. Just by comparing the coefficients of the constant terms, we can form an equation in C, and after realizing the fraction, we can get C is equal to 2 plus 3i. For the last part, let me introduce you to the conjugate root theorem, which we can only use when all the coefficients are real. Since the first root is z is equals to 1 plus ai, then its conjugate z is equals to 1 minus ai will be the second root. Since this is a cubic equation, let's write it out in terms of all three roots over here. Now finally, comparing the coefficients of z squared, we can solve for the third root, which is c is equals to 3. Then just comparing the z terms, we can solve for a is equals to 3, and lastly, comparing the coefficients of the constants, we can get the final answer of k is equals to -30. Welcome to the most difficult topic in H2 math. I hope you're ready to learn vectors, but in three dimensions. For this question, let's try to draw a diagram of the line PQ and the origin O over here. So we can find the relationship between OQ and OP using the ratio theorem, where it's kind of like cross multiplication. So it's 3 times of the opposite side OQ plus 2 times of the opposite side, which is OP, divided by the addition of the ratio, which is 3 plus 2. So adding all of these vectors up and multiplying the 1/5 in, we can get the final coordinates of x. Introducing one of the 2 main concepts in vectors, the dot product, which is basically asking how far apart the direction of these 2 vectors are. The best case scenario is when A and B are perpendicular, where the dot product is 0. If the 2 vectors are in the same direction, the dot product is just the length or magnitude of these 2 vectors multiplied together. And if they are in opposite directions, it's just the negative of the magnitudes multiplied together. To put a more formal definition to it, A dot B is equal to the magnitude of A times the magnitude of B times cosine theta, where theta is the angle between the 2 vectors, and we can form this equation over here if we want to calculate theta. Let's say I want to find the dot product of these 2 vectors. It's pretty simple, where we just take each pair over here and multiply them, and adding all of them up gives us 32. Imagine we have a paper, and vectors A and B lie on this paper. Now the cross product of A and B produces a vector that is normal to this piece of paper and is perpendicular to both vectors A and B. So here's the formal definition of the cross product, where this n hat over here is the unit vector of the normal. Another way to write it is that the magnitude of A cross B is just the magnitude of A times B times sine theta. Let me show you how to actually do a cross product. And don't worry, this formula is given in the formula sheet. By looking at the coefficients of I, j, and k for vectors A and B, we can use this formula to get A cross B is equals to 5, -6, and 2, which is perpendicular to both A and B. An important note is that both the dot and cross product follow the distributive law, so we can expand and factorize them just like algebra, but only the dot product is commutative, because A cross B is different from B cross A, because it's in different directions. So after shifting these vectors to one side and factoring out A, just like algebra, we get the cross product of these 2 vectors to be equal to 0. If the cross product is equal to 0, that means that the vector A is parallel to 3b minus 2c, so we can say that 3b minus 2c equals the sum lambda times A. Since A and C are unit vectors, the modulus is 1, and since the angle of B and C is 60 degrees, B dot C is equal to the modulus of B times the modulus of C times cosine 60 degrees, which is equals to 2. There's this neat little property that the vector dot itself is just the square of its vector's magnitude. So we just transform this vector equation into a scalar equation by taking the dot product of itself on both sides, kind of like squaring both sides. And after expanding it out and using this property, we can sub in the magnitudes of vectors as well as b dot c, which is the same as c dot b because they are commutative. Then finally, solving for lambda by taking the square root, we can get lambda is equals to plus minus the square root of 124. For this question, since we're given the vector OX and the magnitude of OX, let's try to make use of the information that OX dot OX is equal to the magnitude of OX squared. And after expanding out the dot product, and since it's commutative, we can combine the like terms together and sub in the values of the magnitude of OX, the magnitude of A and B, which gives us A dot B is equals to 4. Next, to find the area of the triangle OAX, it's half times the magnitude of OA cross OX, because the magnitude of OA cross OX will be the area of the parallelogram. So putting in the values of OA and OX and expanding it out, we can see that A cross A is equals to 0, and we are left with 3/2 times the magnitude of A cross B. Because we know that A dot B is equals to 4, and by the definition of A dot B, we can connect it to the magnitude of A cross B, where we don't have to multiply the normal vector n inside. So let's sub in the values to find cosine theta is equals to 2/√5, and since we want to find sine theta, we draw the right angled triangle and find the opposite using Pythagoras. Then we just sub in the value of sine theta is equals to 1/√5, and we can get the final answer of 3 units squared. Let's try to use these 2 formulas in this scenario with vectors A and B. So let's drop down point A to get the foot of the perpendicular F, and we want to try to find this length L and the height H. Since this length is the magnitude of A, using trigonometry, we know that L is equal to the magnitude of A times cosine theta, and H is the magnitude of A times sine theta. If we take a look at equation 1, dividing both sides by the magnitude of B, we can get the value of L, which is A dot B over the magnitude of B. And doing the same for equation 2, we can get the value of H, which is the magnitude of A cross B over the magnitude of B. Since theta is acute, A dot B is greater than 0, and we have to take the modulus of this number that A dot B produces. But note that for this H value, it refers to the magnitude of the vector A cross B. Now the equation of a line represented using vectors is R is equals to A plus lambda B. It starts from a certain point A and it goes in the direction vector B, with a parameter lambda determining how long it is. Alternatively, it can also be in this form where A1, A2, and A3 represents the position vector of A and B1, B2, and B3 represents the direction vector B. The angle between these two lines for this question is the angle between the two vectors itself, so we only care about the direction vectors B1 and B2. So for this question, we can extract out B1 over here from the line L1, and since the line L2 is in the Cartesian form, the direction vector B2 is 2, 1, 5. And quickly finding the magnitude of B1 and B2, we can do the dot product between the two direction vectors to get the modulus of -3. Then the angle is the cosine inverse of all of this, which gives us the final answer of 81.6 degrees. Another tip for vectors is to always draw a diagram. So for this question, let's rewrite the equation for line L to be a position vector in terms of lambda. Now our goal is to find the point F, so we know we have to find a specific value of lambda to give us the vector OF. So let's find the vector PF first, which is OF minus OP. Now since PF is perpendicular to the line L, the dot product of PF and the direction vector of L is equals to 0. After working out this, we can solve for lambda is equals to -1. Then the last step is to sub this value of lambda back inside OF to get 5, -2, and 2. As a bonus, we can also find the length of PF by subbing lambda into the position vector PF and also finding the magnitude. It's time to level up to planes! The equation of a plane requires two lines from some starting point A where each of its direction vectors are m1 and m2. Again, lambda and mu are the parameters controlling how long each of these vectors are. So let's try to find the vector AB, which is 2, 1, 0, and AC, which is -1, 0, 5, which are our two direction vectors. And since point A is the starting point, we have our plane equation over here. Now there's another variation of the plane equation which looks something like this. This form requires you to find the normal vector, so to find it, we do AB cross AC, which gives us the normal vector of 5, -10, and 1. For this A variable over here, it's basically a fixed point on the plane, so let's use the point 2, 1, and 4. So putting it all in, r.n is equals to a.n, evaluating out the dot product gives us the final plane equation of r.5, -10, and 1 is equals to 4. To find the point of intersection between a plane and this line, let's rewrite the equation of the line in terms of lambda, kinda like this. Just like doing simultaneous equations, we sub in this value of r into the equation of the plane, and we compute the dot product, and we can get our answer of lambda is equals to 1. Since the equation of the line depends on lambda, we can sub it back into the line equation to get the intersection point of 2, 2, and 4. There's also a formula to find the angle between the line and the plane, where it's the dot product between the normal vector n and the direction vector of the line d. And after working it out, it will give us the final answer of 54.7 degrees. To find the foot of the perpendicular from this point P to the plane, let's identify the normal vector n, which is 1, 1, 0, and then we try to construct this vector PF. Since PF is parallel to the normal vector, it starts from point P and goes in the 1, 1, 0 direction, and our goal is to solve for the value of lambda, which gives us the point F. So subbing this into the equation of the plane, we can compute the dot product, and that gives us the answer of lambda is equals to 4. Then the final step is to just put this back into the vector equation to give us the coordinates of F to be 5, 1, and 3. Now, this is some matrix level stuff, because we want to find the line of intersection between two planes like this. So let's first verify that these two planes are not parallel. Since the normal vectors are not a scalar multiple of each other, we are good. Then we can write the equation both planes in the Cartesian form, where the normal vector are the coefficients of x, y, and z. We can actually use our GC or substitution method to reduce the system of linear equations to get something like this. Now, remember that we want to find this intersection line, which the equation of a line is a plus lambda b. So we gotta introduce in a lambda somehow. Let's try to make the unknown z is equals to lambda. After splitting up into the starting point and the direction vector, we have our line equation. For part B, to find the acute angle between two planes, the trick is to actually use its normal vectors. So using the cosine theta formula and evaluating out the dot product, we can get the angle between these two planes is 40.1 degrees. Finally, it is time to put it all together to tackle this long vectors question. The first step is to rewrite line 1 and line 2 into its vector forms like this, with parameters lambda for line 1 and mu for line 2. And since they cross at B, let's sub one equation into another, and you can see that it forms three simultaneous equations. Our goal is to solve for the three unknowns, lambda, mu, and a. Let's sub equation 2 into equation 1, which gives us mu is equals to 1 and lambda is equals to 2. After subbing those into equation 3, we can get a is equals to 2. Finally, to find OB, we can sub it back into either line, so I'm just gonna sub the values we found into line 1, and we can get the coordinates of B to be 1, 3, and 6. To find the length of the foot of the perpendicular, we could use the equation of the plane similar to just now, but let me show you another method. Let's first find the vector of AB using the coordinates of B and A to get 4, 2, and 4. Since the plane is perpendicular to L2, the direction vector of 3, 2, and 1 is the normal vector to the plane. So drawing out our right-angled triangle, we have AB and N, and we want to find the height h. Since h is AB cosine theta using trigonometry, using the dot product definition, we can sort of derive the formula, which is the magnitude of AB dot n over the magnitude of n. So working out the dot product and the magnitude, we can get the final answer of 5.35. The last part is really interesting. Since these two planes are perpendicular, the normal vector of plane 1 actually lies on plane 2. We also know that line 1 also lies on plane 2, and since we want to find the normal vector of plane 2, we can take the cross product of these two lines, N1 and L1, which works out to be 3, -4, and 1. And finally, because L1 contains point A, let's use that in the equation r dot n is equals to a dot n formula, and we convert it into the Cartesian form to get 3x minus 4y minus z is equals to -15. And that is the beginner's guide to all the JC1 topics. This video took absolutely ages to make. With all the amount of research, studying, and scripting I had to do, I really tried to step out of my comfort zone to try making a H2 math video, and I'm really proud of how it turned out. I hope this video can get you one step closer to passing A-level math with flying colors. Take care, and Axolotl out.